Greetings, welcome to the video on section 4.4 logarithmic properties. Thank you so much for watching this video. I really appreciate you taking the extra time to do this. It'll definitely help us get along in the course how we need to do, how we need to get things done, so to speak. So section 4.4 logarithmic properties, we back in section 4.3 studied some of the properties of logarithms, in particular what the definition of a logarithm was, and we looked at the inverse property to it. In other words, we realized that the logarithm is simply an inverse function to the exponential. In other words, one undoes what the other one did, so that it would be referred to as our inverse property. This is a quick example of that. If I gave you, for example, logarithm base 2 of 8, I can rewrite that as logarithm base 2 of 2 to the third, which says that if I have a logarithm base b of b raised to the x, well, that's just the exponent, which is equal to 3. Similarly, if I had given you 5 log base 5 of 7, well, that's going to be equal to just 7 because the exponential and the logarithm undo each other, all right? So those are a little bit confusing notationally. Take some time to make sure they make sense to you, okay? All right, excuse me. Exponential properties so far, the two properties we have to help us solve or to work with logarithmic equations are this exponential property, which says, for example, that if I've given you logarithm base 5 of 7 to the 6th power, then that's the same thing as 6 times logarithm base 5 of 7. In other words, the exponent can be brought in out front. You can think about this in terms of your properties from exponents to say when you raise a power to a power, you take the product of the powers, okay? And then one of the things that's probably definitely worthy of getting some fresh ink would be the change of base theorem that says, for example, if I had given you logarithm base 5 of 7 and I wanted to get a decimal approximation of that, I can rewrite that as ln of 7 over ln of 5, because that's one of the built-in logarithms on my calculator. Or similarly, I could have used common log, and I could have written that as common log of 7 over common log of 5, okay? All right, so those properties are useful, and we will use them a ton, but they're not sufficient for solving all of the exponential or logarithmic equations that we're going to come across, okay? So we're going to add two more properties to our properties of log, so these sum of difference properties. And these are very valuable. They get used actually in all sorts of places, and you'll see them in calculus again for helping us expand or contract logarithms depending upon what we need to do. And basically what it says is that if you have, say, we'll do this in the calculator just to show you that it's true, say we had logarithm of 5 times 2, right? That can be rewritten as logarithm of 5 plus logarithm of 2, okay? Well, logarithm of 5 times 2, that's logarithm of 10, so that's going to turn out to be 1 on the left-hand side, but we'll go ahead and validate that anyway. So let's get our calculator up here. Okay, so get the calculator up here, and if I go common log of 5 times 2, all right, and I hit an enter, I get back a 1, just as I suspected, and the thing that this property says is that's the same thing if I take log of 5 and add that to log of 2. And sure enough, we get back 1 either way, okay? Similarly, there is a difference property, and the difference property says that if I had given you log of 5 divided by 2, that I can rewrite that as log of 5 minus log of 2. Now, these two properties are analogous again to properties in exponents. If we have the product of like bases, we add the exponents. In other words, if I have a to the n times a to the m, that's equal to a to the n plus m. And then if I have the ratio of like bases, if I have a to the n divided by a to the m, then that's equal to a to the n minus m, okay? And as a matter of fact, the proofs of these two are based upon those properties of exponents. So I'll let you take a look at those on your own, okay? So these are very important properties. We're going to use them quite a bit, but equally important is to realize that the logarithm does not distribute over sums of differences. It's easily confused with these two properties. So for example, if I'd given you logarithm of 5 plus 2, that is not going to be equal to log of 5 plus log of 2. And I invite you to pause the video for a moment and go back and verify that the left-hand side and the right-hand side are equal to each other on this one, and that the left-hand side and the right-hand side are not equal to each other on this one. Okay, so take a moment and do that. I'll wait for you. Okay, we're back. And so hopefully you should have seen that, in fact, that this first one was true and the second one was false, all right? Okay, so now it's time to start your turn. This is getting turned in with your homework, so get out some paper and pencil if you have not already been taking notes, which hopefully you did and got those blue boxes into your reference book. So simplify into a single logarithm using the logarithm properties. Okay, so remember that those properties of logarithms, key thing is that the bases have to be the same, otherwise it doesn't work. So these do have the same base. And so what this says is the property we're going to use, let's go ahead and write it down. We're going to use the property is that the log base b of m minus the log base b of n is equal to the log base b of m divided by n. Okay, they used a's and b's, I use m and n's, but however you want to do it, it's good for you. Excuse me with the coughing, sorry about that. So what's this going to be equal to? Well, this is log base 3 of 32 divided by 4. Okay, now in case you don't remember what 32 divided by 4 is, if you take 32 and divide that by 4, you're going to get back 8. Okay, so this turns out to be equal to logarithm base 3 of 8. And that's as far as you need to take it. You don't need to go any further. If they'd ask you for a decimal approximation, then you would use the change of base theorem or the fancy key in your calculator to do that. Okay. All right, let's keep moving. So simplified to a single logarithm using your logarithm properties. All right, so how do we write this one? Well, okay, I want to do a quick aside on this one to remind you of something that you may or may not recall. And that is, what do we do with rational exponents? So let's say I gave you the nth root of a. Well, the nth root of a is the same thing as a to the 1 over n. In other words, this radical right here is actually an exponent. It's just a fractional exponent. It's, in particular, a fractional exponent with a natural number denominator. So, for example, the square root of 7 can be rewritten as 7 to the 1/2. Those are the same. So keep that in mind. So square roots and raising something to the 1/2 exponent are identical, or just, in sake of completeness here, say the cube root of 6, that would be equal to 6 raised to the 1/3 power, all right? Okay, so back to the ranch here. So simplify into a single logarithm using the logarithm properties. Okay, so this is going to be equal to, using our property of exponents, our property of logarithms, it says if you have r times the logarithm base b of m, then that's equal to logarithm base b of m to the r. In other words, that exponent can be brought in. So that tells me that what? This is logarithm base 5 of 36 raised to the 1/2 power. Okay, now when we know that raising 36 to the 1/2 power is the same thing as taking the square root of 36, so we'll go ahead and write that. If you want to, you're welcome to skip this notational step as long as it makes sense to you, which gets us back what? Logarithm base 5 of 6, which is going to be our final answer. We definitely want to simplify the square root when it's possible. Okay, make sure if this is not a familiar property to you that you've got a spot in your reference book that lets you know that, all right? We're going to need that as we work through these problems. Okay, simplify to a single logarithm using logarithmic properties. Okay, all right. So a good rule of thumb is as always, work with the order of operations. We'll take care of any sort of products using our exponent property first, and then we'll come back and use the sum of difference property. So I'm going to rewrite this as logarithm of x squared plus logarithm of y to the 1/3 minus logarithm of z. All right, cool beans. Okay, so if you want to, it's up to you, just maybe because you want to use the groovy notation, you can change that y to the 1/3 as a cube root and make it look like that, or you can leave it as y to the 1/3. There's actually nothing a matter with doing that. In fact, when you get into calculus, it's preferable to leave them as rational exponents, but just to make it look cool, I'm going to go ahead and put the cube root of y in here instead, minus the log of z. Okay. All right, now let's go ahead and use our product properties. So using the product and difference properties here, notice these are all base 10 logarithms. They all have to be the same base. Check that before you start using your sum or difference properties. The bases have to be the same in the logarithms for the sum or difference properties to work. Okay, so now what? Well, this is going to be in the numerator, we're going to have the logarithm of x squared times the cube root of y. In other words, I'm just combining, oops, excuse me there, hang on. Not an x, a y, there we go. We're just going to take care of this sum first. We'll do that first, and then minus log of z. Okay, so now, using my difference property, that's going to be what? All is a single logarithm. It's a logarithm of x squared, cube root of y, divided by z. So in this step right here, I use the sum property. And then this step down here, I use the difference property. So go back and review those properties, make sure they make sense to you. Okay, so much fun. Let's keep going. All right, use the logarithm properties to expand the expression. Okay, so this time they want us to write it as a sum or difference, and they want us to get the exponents off of the arguments. This time they're using the natural logarithm, or logarithm naturel. So let's break off the denominator first, and so that's going to be ln of a to the negative 2, b to the third, minus ln of c. Come on, we can do this. Oh, come on. There we go. Get the right keys always helps. Of c to the negative 5. There we go. Okay, so this is equal to what? Well, let's keep going with breaking this up. Let's break up this product here. This is ln of a to the negative 2 plus ln of b cubed minus ln of c to the negative 5. All right, so at this point, let's go ahead and use the exponent property and get those exponents off of there. And so this is going to be negative 2. Oh, let's stay consistent. How I'm writing ln? ln of a plus 3 ln of b. And then a negative and a negative is going to be a positive, so that's going to be plus 5 ln of c. Okay, and that's as broken up, as expanded as we can get it. Hopefully these are all making sense to you. They're just going to keep getting uglier, but that's okay because we have got the mad skills. We can do this, all right? So logarithm of x cubed y to the 4th, the 7th root of x cubed y to the 9th. Okay then. All right, so let's go ahead and rewrite this. I'm going to rewrite this. First of all, I'm going to do something with that 7th root. I'm going to make this a little bit cleaner, hopefully, okay? So this is going to be what? This is going to be log of, well, let me just stay the course. Let me just break them all up as sums first. Let's just do that. We can do some more simplifying after we get done with that. So notice I'm breaking up the product into 3 individual pieces at the moment. And then we will deal with that 7th root beast over there in just a minute. Okay, cool. All right, so I broke up the initial products there, did the easy parts, okay? So now let's come in and let's pick off some of the easier stuff again. Here we're going to write this as 3 log of x plus 4 log of y, and then let's get rid of that that 7th root. Let's write that as a 1/7, okay? So that's going to be, I'll take 2 steps here, but if you can do this in 1 step, you're welcome to. I'm going to write this as log of x cubed y to the 9th to the 1/7, all of that in the argument of the logarithm, okay? All right, so now what's that going to be equal to? Well, that's going to be 3 log of x plus 4 log of y plus 1/7. There we go. Log of x cubed y to the 9th. Okay, now I can break up that sum. Now be careful though, because when you break up that sum, you got to put some sort of grouping symbols here to make sure that 1/7 stays in contact with all that, because notice it's 1/7 times that sum, all right? That product turned into a sum via our logarithm properties. So that's 3 log of x plus 4 log of y plus 1/7, and now not half, Mike, 7th, there we go, 1/7 times, and now I'm going to go a little faster here. Hopefully you can see that this is 3 log of x plus 9 log of y. And if you need to, pause the video for a moment and see where that algebra miracle occurred there, okay? You maybe need to do a couple more steps to see how that happened. Okay, let's distribute the 1/7. And if we do that, we get 3 log of x plus 4 log of y plus 3/7 log of x plus 9/7. Did I say 7? Honest. Log of y. Okay, now we can do a little more simplification here. To write this up a little bit cleaner, we can get those logs of x's and logs of y's mixed in together. So if you notice that the first log of x is a 3 log of x, so if I take 3 log of x's plus 3/7 log of x, that's going to be 3 plus 3/7 a log of x, and I want that back as a fraction, which is going to be 24/7. Okay, so that's going to be 24/7 log x. And notice what I did is I added that logarithm and that logarithm together, because they're both, you can think about log x and log x as just being a variable. You can say, okay, that's z, and that's z, so that's 3z plus 3/7z, which is 24/7 z. Oh, let me clean up my 24/7 here. There we go. Okay, all right, same song, second verse. Notice that that's a log y and that's a log y. So if I take 4 plus 9/7, I get back 37/7. So that's plus 37/7 log of y. Now, there are many different ways you could have tackled this. We could have come in and actually simplified the argument of our logarithm and gotten the 24/7 and 34/7 before we started using our sum or differences properties for logarithms. That's up to you how familiar you feel with radical notation and working with that. So either way is fine. If you did it that way, that's just, plum peachy. Okay, now why are we doing this in the first place? Well, we're doing this to help us try and solve logarithmic equations. Okay, now we're going to try and do them exactly, and when we can't, we'll do them with a decimal approximation. But even when we do solve them exactly, we'll also give a decimal approximation to kind of help our viewing public see how things work. Okay, so how would we go about solving this one? Well, let's go ahead and say we take the natural logarithm of both sides of this. So if I take ln, by the way, nothing particular about the natural logarithm. Could have used the common log, and that would have been just fine also. But the main thing is I want my properties of logarithms that allows me to get those x's out of the exponential position. So by taking the common log of both sides of that, that's going to get me 2x minus 5 times ln, stay consistent, Mike, ln of 2 is equal to 3x minus 7 times ln of 7. So that's just using my exponent property of logarithms. Okay, now keep in mind that ln of 2 and ln of 7, those are just numbers. You can go get a decimal approximation of them really quickly here. If I go ln of 2, for example, I see that that's, approximately 0.693, etc. So you got to think about this right here is simply just a number, and similarly, this is just a number, all right? So just as if I had, say, a 3 out in front of these parentheses or a 6 out in front of these parentheses, to get rid of them, I would distribute it. So we're going to do the same thing here. I'm going to distribute my ln of 2. And if I do that, that's going to get me 2 ln of 2 x minus 5 ln of 2. Excuse me, I'm going to go to cursive now because I'm just going to, I've been itching to do it. I'm going to cursive on the ln because it just goes faster, okay? And then I'm going to go 3 ln of 7 x minus 7 ln of 7, okay? All right, so far so good. Now remember, we're trying to solve for x. We're trying to isolate x. Now, minus 5 ln of 2 and minus 7 ln of 7, those are just numbers, okay? So what we're going to do is we're going to go ahead and move those both to one side and get all the constants on one side and get all the variables on the other side. So if I do that, it's going to be 2 ln of 2 times x is equal to 3 ln of 7 x minus 7 ln of 7 plus 5 ln of 2. Now trust me, this is really no harder than solving a linear equation like you did back in elementary algebra. It's just got these funny coefficients. 3 ln of 7 is not a number you usually used to working with. Okay, so subtract 3 ln of 7 from both sides. We get 2 ln of 2 times x minus 3 ln of 7 times x is equal to, and I'm just going to rearrange this so that I have a leading positive sign, and so I'm going to make it 5 ln of 2 minus 7 ln of 7. Okay, now notice that there is a common factor of x on the left-hand side. Let's factor that out. And what we have is 2 ln of 2 minus 3 ln of 7 times x is equal to 5 ln of 2 minus 7 ln of 7. Okay, now divide both sides by this constant right here. We get our glorious exact answer. X is equal to 5 ln of 2 minus 7 ln of 7 divided by 2 ln of 2 minus 3 ln of 7. Now, they may in the book have taken those exponents and used them back here. In other words, had this as 2 to the 5th and 7 to the 7th and 2 to the 2nd and 7 to the 3rd, but the answer is the same. No difference, okay? All right, so let's go check that as a decimal approximation. Let's go ahead and get that. So let's clear that out, and we're going to put in parentheses. We'll put in 5 ln of 2. And then subtract from that 7 ln of 7. And then we're going to divide that. Notice the copious use of parentheses here. Muy importante, okay? And then 2 ln of 2. And then subtract from that 3 ln of 7. Alrighty then. So get back to that decimal approximation, approximately 2.28, etc. Okay, so what I would like to do is remember that number right now is currently stored in the variable ants. In other words, if I come back here and I go second ants, I know I've got that number in there. Okay, so let's take that number actually, just to make our life easy here, and let's go ahead and press our STO key, STO, and then hit your x variable, and it's going to take that number and store it into x for me. So now x is 2.2814, blah, blah, blah. Now, why did I do that? Well, because what I want to do is I want to take 2, and I want to raise that to the 2x minus 5. And then I want to take 7, and I'll raise that to the 3x minus 7. And you go, yay, do the chicken dance, because it looks like it worked, right? It's one of the beautiful things about algebra is you can always check your answers by plugging the supposed solution back into the original equation and see if it made the left-hand side equal to the right-hand side. Similarly, you could have checked it by doing a graphical solution. That would have been a good way to do it too, okay? But I'm not going there. I'll let you do that. Okay, let's move on. So solve the equation for the variable. All right, so again, we want to get this written as a, in some way, a fashion that we can use the logarithm to help us solve it for the variable x, okay? All right, so how do we go about doing that? Well, we can come in and take the logarithm of both sides. But before we do that, I would suggest doing whatever I can to get the constant 8 and 20 as simplified as possible. So I'm going to come in and I'm going to divide both sides by 8. You don't have to do that. I think it's going to make life a little bit easier if we do that. Okay, so 20/8 is the same thing as is what, 5 halves, right? Take 4 into 20 gets you back 5, 4 into 8 gets you 2. So that gets me 5 halves times 1.07 raised to the x is equal to 1.13 raised to the x. Okay, now how do I get those x's out of the exponent position? Well, I'm going to take the logarithm of both sides. Now again, it is your call whether you use common log or natural log. It's one less letter to write down common or natural log, so I will use that. And I also know from experience natural log is the more prevalently used logarithm out there in the real world. So that's ln of 5 halves times 1.07 raised to the x is equal to ln of 1.13 raised to the x. Okay. All right. Now remember that if you have the logarithm of a times b, that can be written as logarithm of a plus logarithm of b, right? You can break it up that way. Okay, so we're going to do that on the left-hand side. So that's going to be ln of 5 halves plus ln of 1.07 raised to the x is equal to ln of 1.13 raised to the x. I don't need that extra set of parentheses anymore. We'll just get rid of those. Okay, now by my properties of logarithms, I get to pull those x's out of there. Okay, yeah, we'll do it now. It doesn't matter, we can do it now. So ln of 5 halves plus x ln of 1.07 is equal to x times ln of 1.13, and there he goes, working in cursive again. That's squiggle as ln, trust me that, okay? All right, so now what? Look at all the x's on one side, all the numbers on the other side, so let's subtract x ln of 1.07 from both sides. So that's ln of 5 halves is equal to x ln of 1.13 minus x ln of 1.07. Okay, so again, we have a common factor of x between these two terms. We're going to factor that out, and we get ln of 5 halves is equal to x times ln of 1.13 minus ln of 1.07. Okay, that's pulling out the common factor of x there. All right, so now I'm going to divide both sides by ln of 1.13 minus ln of 1.07, and we end up with our stunning final solution here. So x is equal to ln of 5 halves divided by ln of 1.13 minus ln of 1.07. And I'm going to leave it to you this time to go in and check that. I want you to take that value of x and plug it in here and here and make sure it makes the left-hand side equal to the right-hand side, okay? If it doesn't, send me a nastygram saying, Mike, you messed up, but I'm pretty sure that's going to work. All right. Solve each equation for the variable. All right, so what are we going to do here? Well, this is kind of crazy. It's like, what do I do? I got x's and my property logarithms, the differences. Yes, I can get them all into a single logarithm. And if I can get them into a single logarithm, then I can solve the equation. So notice in the previous problems that we worked here, these were exponentials that we applied the logarithm to both sides of the exponential to be able to solve the equation. So in problems 28 and 30, we were given exponentials and we used the logarithm to help us solve them. Here, we are given logarithms, so we're going to use the exponential to help us solve them. But in order for us to do that, we got to get it into a single logarithm first. So on the left-hand side, we will go ahead and use our property logs here. And so this is the logarithm base 10 of x plus 5 divided by x plus 2, and that's equal to 2. So all I've done so far is just use, logarithm of a over b is equal to logarithm of a minus logarithm of b. Just use that property, okay? All right, so now what? Well, this is the exponent of 10 that gets me x plus 5 over x plus 2 is equal to 2. In other words, 10 to the second is equal to x plus 5 divided by x plus 2, or better known as 100. So that's going to be 100, and if I multiply both sides by x plus 2, that's going to be 100 times x plus 2 is equal to x plus 5. By the way, just so we know here, at this point right here, you know x cannot be equal to 2. That's, excuse me, negative 2. That would cause division by 0. So make sure you keep that in mind as you're working along. We're going to have to go back and check our answer anyway, so not too horrible. So that's going to be 100x plus 200 is equal to x plus 5. Okay, so let's go ahead and subtract x from both sides. If we do that, we get 99x plus 200 is equal to 5. And we'll subtract 200 from both sides, and we get 99x is equal to minus 195. And then divide both sides by 99, and we get x is equal to negative 195 over 99. All right, so we need to go back and check that and make sure that actually works, okay? In other words, does it actually give us a solution or not, okay? It's really important that you check your answers when you're dealing with logarithms. So let's go ahead and clear that. And let's go ahead and take our answer here. So negative 195. And then we will divide that by 99. And we'll stow that into x. Hit and enter, okay. And so now we're going to come in and see if that actually works. So you're going to take log of x plus 5. Notice x is negative 1.96 blah, blah, blah right now. That's what we did by storing it there. Plus 5. And subtract from that logarithm of 2, or x, excuse me, x plus 2. And if the gods are with us, it's going to come back 2. Bada bing, bada boom, it worked, okay? So you need to do that. That's not optional. You need to go back and check your solutions once you've got them, okay? Muy importante. Solving logarithmic equations is fraught with danger if you do not check your answers when you get done. Okay, so solve the following equation for the variable. All right, let's use our properties of logarithms here. So this tells me that what? This is ln of x times x minus 6. Because I have a sum here, I change that into a product, and that's equal to what? Ln of 6x. Okay, so now what? Well, notice I have a logarithm on the same logarithm on both sides. So I can think about this as simply take both sides and use our properties of bases. In other words, say raise both sides so they have the same base e. In other words, there was a property we did early on that said that if we had a to the x was equal to a to the y, then that meant that x must have been equal to y. Well, you can go the other direction with that. So you can say if I got x is equal to y, then I can say then that must have been a to the x was equal to a to the y. So now you pick your base judiciously. In this case, I pick e because I know that they're inverse operations to each other. They knock each other off, and I get x times x minus 6 is equal to 6x. Okay, so now what? Well, that's the same thing as x squared minus 6x is equal to 6x. Subtract another 6x from both sides of this because we've got a quadratic, which means we've got to get it set equal to 0. And we get x squared minus 12x is equal to 0. So factor out the common factor of x, and what's left behind is x minus 12 is equal to 0, which gives us two possible solutions. We get x is equal to 0 or x is equal to 12. All right, now you're not done. You have to check your solutions. It's not an option, okay? So let's go check. And so we got x equals to 0. We'll check that as our first solution. And we get ln of 0, whoops, minus ln of 0 minus 6, whoops, is equal to ln of 0, or 6 times 0, right? Oops. Those are all big oopses. Why? Well, hopefully you remember something about the domain and the range of the logarithmic functions. But just in case you don't, you can go check it on your calculator. You go ln of 0. And it goes, yeah, no, error domain, not a valid enter. Yeah, you can't do this. Don't ignore the rest of that stuff, all right? So ln of 0 is undefined. If you think about the graph of the natural logarithm for just a moment, remember it was the inverse graph of the exponential. It has a vertical asymptote at the x-axis, excuse me, the y-axis, doesn't it, right? Okay, so that's a rather rough sketch of the ln function. Okay, so that one doesn't work. Okay, so let's go try 12. So ln of 12 plus ln of 12 minus 6, is that equal to ln of 6 times 12? Okay, so let's see. Well, this is ln of 12 minus 6, same thing as ln of 6. So I'm going to do this without even using the calculator to show you that indeed it is true, because ln of 12 plus what? Ln of 6, right? Is that equal to ln of 6 times 12? And yeah, you can stop right there, right? Because that's our property of logarithms. It says that if you have a sum, you can rewrite that as a product. So yep, it does work. Bada bing, bada boom. But hey, go get a decimal approximation and check both sides that those work too. That's not a bad idea. It's worth a few electrons to do it. Okay, so that was a lot of information really fast. Hopefully this gets you a good go on the homework and you can get going with it. Do not be shy about posting things up in the Q&A form. Keep in mind that we do have an opportunity on Thursday, and so your focus really should be for prepping for that opportunity and tackle this stuff over the weekend. This is when you need to be working on these problems. So you can save this video for watching over the weekend, which would have been nice if I said that at the beginning, right? Or you can come back and rewatch it when you need some help, okay? Thank you very much.